Hello, everyone. My name is Sam Reynolds with IBM, and I have the honor of introducing today's webinar, which is called in your registration All Aboard the Network Express, which is a nice catchy title for what the title you see here, which is support for the Network Express feature on Z17. Our speakers today are Jerry Stevens and Randy Kunkel. We do want to point out that on the title chart here, you see a URL that will take you to slideshare.net, where there's a PDF uploaded of these charts. So if you want to have those to follow along, or you want to have them afterwards, that's probably a great thing to do. So write that down real quickly. It should be pretty easy to remember. And with that, I'm going to turn it over to the first speaker, who will be Jerry.
Thank you, Sam. So good morning, good afternoon, or good evening, depending on where you're located. Thanks for joining us. And so Randy and I will take you through this presentation today. Here's a quick look at what our agenda looks like. I'll be taking you through the overview, which will cover the system architecture and the solution itself. And then Randy will take you through the details of how to configure it, both in the I/O configuration, the stack, and a thing we call auto migration will be an interesting aid for how to get to Network Express. And then we'll look at some sample displays and talk about where we ended up with current limitations in terms of functionality that might be staged. And then Randy will also talk about the APARs and configuration to get you started. We also have an appendix, which we probably will not cover today, but in that appendix, there's very good examples, the sample displays, some HDD configuration examples. And there's also a very nice long chart that shows the comparison, side-by-side comparison of the OSD configuration versus the new adapter. So with that, so let's talk about the overview of this topic. So the IBM Z17 was just recently announced, and it introduces something called an I/O data processing unit. And that I/O DPU comes along with new system architecture and a new network adapter called the IBM Network Express feature. The Network Express feature combines the functionality of both OSA and RoCE into a single feature. And you can view this as, well, this is just my next generation of OSA, or it's my next generation RoCE. And for the most part, that's been our objective, is to view this as next generation, and how you get started, how you use it, will look and feel pretty much the same as you have for years. ZOSCOM Server has provided support for the new feature, and it's available on Z17, and this is what we'll talk about today. Our focus is what did COM Server do for this machine and this feature. And in this presentation, it'll be an overview of the system and the feature, along with the system architecture. It'll be a high-level overview of that. And then we'll talk mostly about our support, what we do to provide the support to you. And then what's really different to you? What do I have to do to configure it? Is it look a lot like OSD, or what are those differences? And we like to show you some of the usability simplifications. So part of our focus is, if we give you a new OSA, what can we do to make it easier to use it? And I'm hoping that you will agree that we have some usability enhancements in here that you might like. So let's start by talking about the problem. Why are we here? So what happened, and why did we have an I/O system transformation? Why was that necessary? So for years, the I/O subsystem of IBM Z is built on solid architecture. Some of you might remember it as channel architecture or CCWs, but it has a rich history of storage and networking I/O functionality, throughput, bandwidth improvements, intellectual solutions that provided creative solutions for System Z. And all of this while maintaining application backward compatibility. So the applications, they don't see the difference as our hardware has evolved over the years, but basically provided rich functionality over the various generations of Z. But at some point in time, we bumped into some limitations, and the current I/O infrastructure was constrained in terms of being able to move forward, to deliver improved latency or additional bandwidth capability, or even to provide enhanced functionality. We were running into limitations with the system architecture. And without some changes, the current physical packaging and cases of network architecture, those changes were not going to be necessary. And on the right there, you'll see we have a very high-level drawing of what we have today. And today, is a reminder, in the mainframe, you have a processor complex and you have system memory. And we travel across a PCI bus to get to our I/O drawers. And there we have various I/O cards. In the case of networking, we have basically what you would think of as the OSA Express infrastructure. And there we had an ASIC, and on that ASIC is where the OSA firmware would execute. And so every time the OSA firmware would have to reach into system memory, it would have to traverse that PCI bus. And that's how data came across off the wire through this converged network adapter, which could be storage or networking, and it would travel through the I/O drawer to the drawer for where your processor and memory was. And that latency was starting to become a problem for us again to move forward. And to solve this, we realized it wasn't going to be a minor change. It was going to require some re-engineering of that I/O infrastructure. And on the right, we show you what's new now. And so the ZIO side that we show you is where we move that ASIC functionality. It's now resides in the processor complex. So that's where that ZIO really means the DPU. And so there's going to be on System Z, there will be a DPU for AI, there will be one for I/O. And so both networking and storage will use this new architecture. And it provides many enhancements to us. It gives us it builds new functionality and possibilities for the future. And one of the things you'll notice right away is to reach into memory. It's very much more efficient and will be L2 coherent with the memory in terms of every time we have to access the memory now, we do not traverse the PCI drawer or the PCI bus. So we reside right in the mainframe with memory. So as we move data in and off the platform, it's much more efficient model and builds for the future. And so we still go through the I/O drawer to get through a switch and get to an adapter and get to the LAN. But everything that we process for Z in the I/O infrastructure will now reside in the processor complex. So the OSA firmware executes on that box you see right there in pink. So let's look at Ethernet today. So Z currently has several Ethernet cards or adapters. And you'll see the operating systems are ZOS, ZVM, TPF, or possibly Linux. And what you'll see is that, okay, we have several forms of OSA, or networking, we should say, that flow some protocol to get onto a LAN. And each requires a unique channel type and a unique network adapter. And for the networking team, we think of it as OSD, which supports general IP, which is things like TCP/IP or UDP. We have a console controller functional card, which is a separate Ethernet card. And we also have a separate card for RoCE, for RDMA protocols, such as SMC-R. So as you look at that drawing on the right, you see, okay, that's taking up some space in my drawer. And then when you consider redundancy requirements and virtualization requirements and bandwidth, then that number of cards can add up. And we actually have seen customers run out of card slots, so they would like to add something else. But when you add storage along with the networking requirements for your I/O drawer, you can run out of slots, switch cables and ports, and it can run our customers' expense up as well. So what we do with the new card here, it's viewed, we title this as a converged multifunction network adapter. We're trying to eliminate the number of cards required just to access Ethernet. Now, we've not converged storage and networking to a single card. They're still separate functionalities, but here we're focusing on just networking. And on this chart, we call it OSH or RoCE combined. And so what we've introduced is the new card, the Network Express, which we'll be discussing. The new channel type or chiplet type is OSH, and it means OSA for hybrid. So hybrid just meaning that it has multiple protocols that it will support. And we'll still carry forward the terminology of OSA, OSA meaning your networking card, open system adapter for hybrid solutions. And it will have a new system architecture that's very much like QDIO, but it's called Enhanced QDIO. And we'll talk about why it's enhanced. We carry some of the features forward, and some of them are completely different. Now on the RoCE side, there's a new FID type called NetH, and that's for solutions for like SMC-R and native PCI. For example, you'll see that Linux will use the card for native PCI access. ZOS will use the card for OSH channels. ZOS will also use it for RDMA solutions like SMC-R. So some of the key characteristics of this new card, it's multi-function networking adapter, and we intend to plan to do this going forward as protocols are added. The physical card itself has 2 ports, 10 or 25 gig, and each port will be separated. So when the card will look like 2 cards logically, but it will take 1 card slot, and each P-CHID will have a single port. And I'll talk about this more in just a moment. But so logically, it'll look like two cards, but it'll be one physical card. Multiple protocols can share the same physical port. So I could have one port being used for standard IP, and one of them, and that same port could also be used for RoCE itself. Each port can be configured to provide a single function or combination depending on what the user has in mind there. LPAR to LPAR traffic is still supported through shared adapter. And while it's doing this, it preserves all of the offloads, segmentation checksums. So that's new we did not do that in the past. So we're hoping that we will see improved benefits with the new LPAR to LPAR traffic. And then there's some footnotes down at the bottom that I want you to take note of is, for example, the cards are all optic. I believe SR and LR supported. We'll continue to support QDIO on this platform on the older cards. But again, we encourage our customers to move forward with OSH. Linux will access this card using native PCI. It'll use the NetH function. And we're not showing OSH here. That will remain as a separate card. This is just networking only. So EQDIO. Now we have a few charts that will talk about EQDIO, but it's important to understand some of the key differences. And here on this chart, we try to just point out the main concepts. So OSH uses Enhanced QDIO, and EQDIO defines the interface specifications between software and firmware. This is how z/OS manages and communicates with the card. Again, very similar to QDIO. But some of the key differences are, and this is very important to understand, we're going to say it over and over. But first of all, EQDIO operates at layer 2 only. So this notion of a QDIO header and routing packets based on IP addresses, et cetera, that does not exist anymore. So everything is based on a virtual MAC, layer 2 only. So as packets come on and off the card into z/OS, they are fully formed IEEE 802.3 standard Ethernet frames. So that's different. In the past, when the packets would arrive in z/OS, they would have a QDIO header, and the adapter itself would transform them for us. That transformation is gone. OSH interfaces require a virtual MAC then, so the VMACs are no longer optional, and the whole concept of turning a VMAC off and using primary-secondary router, that's gone. So primary-secondary routing functionality is gone. Every interface will have a VMAC. IP assists and TCP offloads, of course, those things are cost savings functions that still will be available. They're very important to z/OS customers. And so what you'll see is that bullet seems to contradict the pure layer 2. So we are pure layer 2, but we still get our offloads and assists. You might recall the thing called MPC architecture. This is multi-path channel support. That's been eliminated, and that will become a pretty important point, which we'll make over and over. And that gets rid of the multiple devices just to have a single interface. This control read and write devices go away, and we'll use control queues instead. And so now every interface is just a single channel device number that's used, and the whole multi-path channel is eliminated in terms of an interface. Now, we can share the card, and every interface will have a device, but they will not require multiple devices. And so that's a simplification functionality that will end up being of great value. Each IP interface into OSH, again, uses a single versus the 3 devices. And LPAR to LPAR traffic is supported, and again, preserves the offload. So that's an important cost savings advantage. Now, some of the key concepts and terminology that you'll hear today is new Z17 network feature, again, is Network Express. Now, because OSA Express will coexist on Z17 with it, there will be, you'll have to get used to the terminology. Are you talking about OSA Express or Network Express? And so here today, we're focusing on Network Express. Again, supports 10 and 25 gigabit. All ports are optical, and SR or LR optics are available. And the default of the MTU of the new card is Jumbo Frames 9000. But how you define and configure your MTU has not changed. It's just it defaults to the optical value for the speed of Ethernet. But if you set a lower value, of course, those settings still take place in the same way. Each P-CHID import supports 2 personalities. You can configure one or the other or both, what have you, but you'll have an OSA personality for standard Ethernet. It'll be defined as an OSH channel or chiplet, defined with channel devices. On the other hand, you could also use it for RoCE, for RDMA, for SMC-R protocol. And it uses native PCI architecture. It does not use EQDIO, just like it does today. It's defined with function IDs or FIDs using a new FID type called NetH. NetH supports native PCI functions such as RoCE or standard Ethernet, which will be used by Linux. Again, Linux will use the card using NetH, not EQDIO. The ZOS for IP will use EQDIO only and NetH only for RoCE. Now for EQDIO, again, the architecture is a big part of this. It's included here again. It's somewhat redundant, but I want to make sure everyone catches this. It's layer 2 only, but the IP assists are still there. All packets come and leave ZOS in fully formed frames to expedite the transmission and reception of data off the LAN. And again, it does not use MPC, which is really going to be a simplification item in terms of how many devices you need and how you configure them. And number 4 is, I would like to have a drum roll, but we don't have one here. But nevertheless, the guys were able to eliminate the VTAM TRLE definition. So that's going to be a big usability improvement. So dynamic TRLEs are still created to make all the operations and commands still functional, but you no longer define the TRLEs yourself. They'll be dynamically created. So once you get your HCD configuration configured, you'll point to that device on your interface statement and we'll dynamically create the TRLE. So that's a significant improvement. I think you'll enjoy that one. So big picture, let's look at the comparison. On the left, you'll see OSD. It uses QDIO architecture versus the right. You'll see Network Express. Its channel type is OSH, and it uses EQDIO architecture. On the left, you'll see that when we had 10 and 25 gig OSAs, it was a single PCHID with a single port. But on the right, when you get a Network Express feature, it will have 2 ports, but you have to view them as you manage them, as the card is managed as 2 logical PCHIDs. So all our pictures in here will show adapter with single ports. We're talking about a PCHID. Or now in software and operations, we operate with channel IDs or CHIPIDs, but PCHIDs represent a logical card. And here, when you slide in a new feature, you get 2 logical cards. Each of them will have a single port. You'll no longer configure port numbers anywhere for Network Express, not in the operating system, not in HCD. A PCHID is a single port. That's all you need to know. You don't configure it anywhere. It's always port 1. Both PCHIDs on the native Express must be the same type. In other words, you can't mix the physical port like an SR and LR. So the ports are the same type on the card itself. And I think that's everything. So again, each port can be configured to use a channel type OSH or RoCE or both. So it's depending on how you need to use that port. So looking at the same view from the RoCE perspective, on the left, you see the old FID type RoC2. On the right now, if you want to use RoCE, you would configure a FID type of NetH for the new card. And then you'll see underneath each of those, you'll see the old RoCE on the left. RoCE Express FIDs are defined as RoC2. All FIDs and virtual functions are defined on a PCHID and port basis. Now, again, that's going to go away. Any OSA IPQENet interface can use any valid RoC, so you can point to any card. Now, on the right, when we get to Network Express, the Network Express RoCE PFIDs are defined as NetH. Management of RoCE PFIDs and resource groups is eliminated. The physical function is now within the OSA firmware. So that parenthetical is a big deal. That means the PSP, the PCI support petition is eliminated for managing the new RoCE cards. The management functionality is in OSA itself. No more port parameter required anywhere, so you can't configure it. It's obsolete because a PCHID is a port and that's it, 1 for 1. ZOS Comp Server SMC-R config is unchanged. So how you configure it, look at it, looks very much the same. I point to it, but the only difference now is that because the functions are converged to a single port, is that when you configure your PFIDs on your interface statement, it must be the same PCHID. So in other words, for OSH, your interfaces have to be converged to the same physical port. You can't just port to another one. If you move OSD and you use it on Z17, you will have to point to, it's required to point to one of the Network Express NetH PFIDs. But for OSH, the NetH FID is on the same physical port. They're always converged. In terms of operations, in terms of online, offline, there's nothing changed here. but we'll add this chart. Your IO configurations step is required. It will be different. We have samples in the background, but you can configure your devices and provide them to us. But the step of configuring a TRLE to match those devices is gone. You don't have to do that any longer. But prior to starting your interface in TCP/IP, the devices must be defined and online. And if there are no OSHs defined, then the TCP/IP start will fail. So if you start an interface and nothing's defined for OSH, of course, there's nothing to wait for. It doesn't exist. That will fail. If there are no OSH's devices available, they're defined, but they're not allocated, then TCP/IP start interface will fail as well. So basically it's defined, but nothing's available. Can't wait for it because there are none available. It's 2 and 3 are very similar. If there are OSH devices, but they're just offline, then the start of that interface will wait, and it supports dynamic ENF. It'll wake us up when a device comes available that's comparable to OSD. So again, in the backup, we have, in the appendix, we have examples of the displays and the configuration. Here is an example of displaying a channel. Here we're displaying channel 9, chiplet 9, and you'll see it comes back as a new type 35 with a new description that is OSA hybrid. And you'll see that it's, in this example here, the device is 2 Baker 7, and we have 0, 1, 2, and 3 available in line. So if you're starting an interface and it doesn't start, you need to confirm that you have the path and the device is online. And this is really no different than you had in the past, except for OSH. You now need to have an OSA hybrid channel available to you. As far as the PCI devices, again, it's very similar. There are no ZOS operational changes used in terms of how you use PCI devices or RoCE. RoCE H interfaces that are defined with PFID and SMC-R IP addresses, that's SMC-R v2, are dynamically started with the start of the OSH. So if you start your OSH interface and you have those parameters on your interface, we'll dynamically create the RoCE interface as we always have. If the PFID is not available offline, for example, when the interface is started, then the RoCE interface will not be started. If the PFID subsequently becomes available after you started your OSA interface, then the dynamically defined interface must be manually started. So you have to use this naming convention and start your RoCE interface manually. And again, that naming convention is described several places. So there, again, there's a sample in the appendix of this as well. Displaying the devices. So there's 2 types of displays here for ZOS administrators. There's display PCIe, and it displays all of them. In this example, it shows there are 2 PFIDs. They're defined as Network Express. In this example, they're configured, and they have a PCHID value of 2 Fox Charlie and two function virtual function numbers of 1 and 2. If you want to drill down on a specific PFID, you can add that on the display dspace PCI comma PFID 501, and it will give you more details about the 501 PFID. It shows you a little bit more detail there that it is virtual function 01. You have no operations or requirements to know that other than just how you've configured it, but you do need to know the PFID is the one you expected to use. The PNet ID is also shown on this display. So many times our service groups might ask you to display the PFID to see, well, what did you configure for PNet ID? And some of you might be thinking, or you might be ahead of me, that, wait a minute, why is there a PNet ID? Didn't that go away if it's a single wire? And we're going to tell you, no, it doesn't go away, because the PNet ID is actually used for various functions. And it's very dynamic in terms of its need. And it need changes for like failover scenarios, et cetera. So PNet ID for these adapters are still required. Okay, so this is my last turn. I'll turn it over to Randy where you get the details. And this one is just to show you the configuration. So, and Randy's going to take you through how you configure it. So again, OSD, we had our IP QENet 6 interfaces for configuring those channels. And so for OSH, for EQDIO, we'll have something very similar called EQENet or EQENet 6 interface statements that we've introduced for OSH. And RoCE v2, again, the PFID parameter of the interfaces, which it dynamically creates those interfaces. They get created for you as a result of starting the IP interface. And so ZOS TCP/IP adds those new support for these new interface statements. They'll look a lot like the older interface statements, but in a simplified form. Randy's going to take you through the simplification.
All right, thanks, Jerry, for a great job. So we'll start out with a review of how OSD or OS Express works today as far as TCP/IP configuration. Maybe if we start at step 1 in your HCD or IOCDS, this is where you're defining your devices. You can see here the system admin set up at starting with channel or device number 2.00. He set up 16 devices of type OSD. And then the system admin would have to take those devices and define them in the VTAM TRLE next. And as Jerry mentioned, this is OS Express where you had control devices. So you minimally needed at least 3 devices, 2 for control path, read and write. And then you'd have basically a data path device for each of the interfaces that utilize it, plus 1 for NTA if you needed that. And then at that time, you'd have to define a port name, and that port name, in this case, is OSA port 2dog. That would have to be correlated with your TCP/IP profile and to set up that. So basically, in the TCP/IP profile, you had IPQENet statement. When you did the start command, during that activation signal, it would pass that port name over to VTAM. VTAM would find your TRLE, and that's how it would find what devices to allocate for the control path, and then assign one of the data paths in any random order for the, it's basically top down for the interface being activated. So one data device, and then any interface being acted by a stack in a common INET that uses that same TRLE port name definition would just use one of the other data paths and share the control paths for configuration. So here's backing up the current IPQENet definition. And behind that, the basics is IPQENet, and you specify the port name. And in this case, you can see there's a chiplet type defaults to OSD, and then there's OSD interface definitions. And there's a long list, and we're going to get on in about 3 or 4 charts. We're going to list what makes sense on a new thing, on the new EQENet definition statement. But the biggest thing here is that you had a port name that defines that, and that tied to the TRLE. We kind pretty much at the bottom of the page is going through many of the steps that we talked about on the prior chart. But the one key thing is that the devices are kind of arbitrarily assigned in the data paths once there's no affinity between interface A and one of the data devices. It just picks the first one available. And that's kind of how the new EQENet interface operates as well. Okay, so now interface simplification. Jerry already mentioned that the big wow factor is that we eliminated the user-defined VTAM TRLE, so that's out of your control now, and we take it into hands. Basically, when a stack starts, it passes the TRLE, or I'm sorry, the device number that you defined in your EQENet interface, and we dynamically allocate one of the devices and dynamically build a TRLE that represents that for VTAM. So that's out of your hands. That's not something new. That's a concept that we, kind of just ran off of from hypersockets, ISM, and RoCE. They all are also dynamically built TRLEs. If you want to display those in the VTAM world, you can do there's a major node called IST TRL, and that's where all dynamic TRLEs are built and managed. Okay, so for simplicity is one of the main games here, along with performance, is basically you're going to find that the new EQENet interface is a dumbed down or smaller subset of the parameters that we used to. We took smarter defaults, and basically the biggest name change is IPQENet turns into EQENet, and port name is now dev number. That's basically the difference. And you'll see that we're not introducing all new parameters. It's very much the same set of subparameters and less of them. We just took smarter defaults, some of them, so the parameters kind of go away then. So the dev number, it can be any device number that you define in HCD, but we prefer that you use a consistent value when you're coding them, since it's really just a way for us to get to the PCHID of that adapter. So, and then we query the iOS subsystem to find out what devices are actually available and pick the first online available device to assign for that interface. You'll see that as you share devices on a single stack for that port, that you'll have to do that, or we'll catch you and we'll get to that page coming up. And then I've already mentioned this, that many of the legacy parameters that are either replaced with, like, port name is now dev number, or they're integrated as the base defaults of the new EQDIO architecture and the EQENet definition. And we took basically smarter defaults. Jerry and I have been going to share many years, and it's basically, touting our wares and all the new enhancements that went in over the many years. And most of them aren't defaults. And at the end of the presentations, many customers are always like, how come that's not the default? Well, now they are. We're at a new venture in life, and the EQENet is like a brand new adapter, brand new machine. It made sense to pick the smarter defaults, and that's what we did. Okay, so now in a new world with Enhanced QDIO Ethernet, the OSH configuration, you still start an IOCP or HCD to configure your OSH devices. In this case, the system admin set up 16 devices starting at 2FOX00, PCHID 84, or chiplet 84. And the nice thing here is that there's no you don't need a VTEM TRLE anymore. We took that for, it's still there. If you want to display it, you can. And the ending name is IUTE, and then it's the device number that we selected for you. That'll be under the IST TRLE major node. And basically, if in your TCP/IP profile, now you define EQENet dev number 2FOX00. And that, as I said, 2FOX00 doesn't mean that that's the one you're going to get. It's going to be 2FOX00 or through 2FOX0FOX, any one of those that are available, but it's pretty much first come, first serve, and they'll get them in that order. So now this is kind of a high level look at the new EQENet interface, or EQENet 6, and basically the port name is now dev number. Pretty simple, and then there's common parameters that are going to look very similar to the IPQENet ones that we showed earlier or mentioned earlier, and then in the next slide we'll get into the specifics of what applies and what doesn't apply. I think that's, essentially it's basically dev number replaces port name. It's as simple as that, and IPQENet turned into EQENet. There is a footnote at the bottom that says a dynamically generated port name is created for each OSH interface. That's pretty much, and you'll see it in some displays, but it's not the port name of the old where there was like firmware checks that if two guys or two different stacks are sharing the same physical port that they had a match in OSA firmware. Nothing like that. That's for a future enhancement that we may need for OSA NTA to add that. Okay, so with the new Enhanced QDIO Ethernet interface parameters, which ones are relevant? What's obsolete? Let's start with that. So chiplet type. Of course, there's a chiplet type. It's OSH, but since there's only one type of chiplet, it seemed not essential for us to have you specify OSH since that's the only one. OLM, that's kind of a niche or an edge case optimization that doesn't apply anymore, along with primary, secondary router. Jerry mentioned that VMAC is required for that, so primary and secondary router does not apply anymore. Dynamic VLAN registration is no longer necessarily required. We still support statically defined VLANs, of course. So here's a big one, read storage. So in the past, you were required to set up how much memory. It takes defaults like min or max values, and it's basically, it's either about 4 meg or 8 meg per inbound read queue for the device. And many customers, just out of fear of how much, fear of losing packets because there's not enough reads being replenished, because it's kind of a race condition as data is coming into these physical ports, the NIC's offloading and tapping the ZOS communication service to pull this data and process it inbound, all the same time trying to replenish the reads that just were used up with inbound packet flow. So a lot of customers just maximize these out to 127, what's called S-balls, and then you had to use a plethora of different ways to configure that. But we took that out of your hands. As part of the simplicity, we dynamically allocate what you need or what we think you need on your behalf. And we have some cool charts to show you on the TRLE, how you can actually see what we're using. But basically, and then before I get there, another option is the inbound performance, where this is one of the items that we allow multiple input queues for different types of workloads, right? For ZCX workloads, we can offload work to the zip engines. Same thing with IPsec. We have specialty processing based on basically the work coming inbound. And OSA does all the work by separating that traffic and delivering on specific read queues for us. So now, going back to the read storage allocation, for sure you're going to get 2 queues built for you. You're going to have the primary queue, which is the default queue basically, and then you're going to get the bulk queue for like streaming workloads. Those queues all default to 8 meg. And then all the other queues that are instantiated once we recognize that you have enterprise extender work or you have CCX work or IPsec, et cetera, those all start at a 4 meg ring size, but they can dynamically expand and contract based on the workload. And we handle it all for you. And you can see at any given time from either your NetStat DevLinks display, we show you a one-stop shop of the total read source for that device. And on the TRLE side, if you want to drill down into each specific queue, you can actually see what the history of that queue was. So we'll get there, and that was a big wow factor of taking that off your hands. So what makes sense? What was replaced or refactored? VMAC is now required. That existed before, but now you have no choice. That is the default. Subnet mask, you must configure subnet mask for the new OSA EQNet parameter for IPv4. And port name is now introduced, that is now being replaced with dev number. That's the big change between IPQENet and EQENet. Okay, so what's remaining? So new OSH parameters, type, of course, EQENet. Dev numbers now introduced. And again, that's just the lead device that we recommend for that PCHID. And all the rest here on the existing, or these are all remaining parameters that made sense to use. IP address, of course, with the subnet mask is now required, all the way down to MTU, SMC-R, SMCD, same defaults as before, but these all made sense to carry over from the old configuration. But nothing new other than dev number and EQENet. Everything else you should be comfortable with from your old configuration. And I'm going to have some side-by-side displays of a current configuration of what you might code as IPQENet and what it looks like today with EQENet. Oh, thank you, Jerry. So at the very bottom of the page, just to point off, all these start options in the TCP/IP profile: segmentation offload, checksum offload, auto IQDC, QDIO accelerator. They're all one-stop keywords that both apply to OSA Express as well as Network Express OSA. So we didn't introduce new keywords for one for OSA, one for the new OSA. It all applies. As Jerry says, this is basically your new OSA, and it should look and feel just like your old OSA. It doesn't change. They all play in the same sandbox. They could work side by side together, separately, whatever you configure. We don't, favor one over the other. If you had an OSD and an OSH configured in the same LAN group, they work and play together as well. And these, as Jerry, these important offloads, checksum and segmentation also apply. OSH OSAs now, they can play with, you can still use SMC-R technology. You can still use auto, hypersockets converged interface, all that apply. QDIO accelerator, that's another great performance option. Those all apply. So one caveat on QDIO accelerator, we have two accelerator tables, one for the old OSA Express that routes, inbound from OSA to hypersockets or OSA. And now we have another accelerator exit that's all EQDIO to EQDIO. So they don't play well together as far as that goes. They have their separate worlds for QDIO accelerator logic, but we certainly did preserve the functionality. And one thing about accelerator is for the hypersockets converged, or for the OSH side, we only support Enhanced QDIO to Enhanced QDIO. We do not support Enhanced QDIO to hypersockets. That's one use case that we could not get to, but it's still under consideration. Okay, so I kind of alluded to this earlier, the DevNum design usage rules. So, we've already gone to the point that it's just for high availability. We use that as a starting place to get to the PCHID, to find all the devices that are defined for that LPAR to use, and we just picked the first online available one. In the NetStat DevLinks, we showed with what you actually configured and the actual device that we selected for you. So you'll be able to discern which one you are using. And a reminder that port number is no longer applicable. It's just always logical port 1. And here we're getting into the rules of why. So if you had two devices, so in the old world with IPQENet, you could have multiple devices that supported different VLANs like VLAN A, B, and C in a single TCP/IP stack, and you had port name that actually tied it together. So when TCP/IP is processing the profile, it knew that you had the same port name, that it could like monitor rules or enforce rules, and the rules of sharing a port for an IPQENet are the same rules that apply to EQENet. But we were at a disadvantage because we don't have port name anymore. We have a dev number. And if you coded different dev numbers, we wouldn't know that you're tied to the same physical port. And that was our, one of our reasons for that. So why you always code the first dev number, number one, is just clean and easy because you're not really getting the device you pick. So it's just easier to pick a consistent value for all your devices, whether they're in the same stack or different stacks, and we'll figure out which one's available. But it also allows us to know that it's the same physical port and enforce the rules. So if you honor that, then we could detect any errors in profile processing. If you cheat and put a different dev number, we'll find it at activation and enforce the rules, and the second one won't activate. So the configured dev number must be all the same. That kind of gives us what I was telling you, that we know it's the same physical port then, and we can enforce the rules. You have to have a unique subnet and a unique VLAN per interface if you're sharing the same port for OSH. VMAC route all must be configured, and that's it. And then the maximum number of interfaces that are supported per IP protocol is 32, quite a large number, the same as IPQENet. And again, just these are the exact same rules that OSD supports today. We didn't make any new rules. Okay, so Jerry mentioned on the intro chart, what's on the agenda. There's a new thing called, you have the choice going forward of, you're getting all new hardware, and generally customers don't like to configure making software changes at the same time. But so since you have a new OSH feature here, now you don't have a choice, but you have a choice in that you can actually tweak your old definition if you feel more comfortable doing that. When you see the side-by-side comparisons between IPQENet and EQENet, you're going to say, oh, that's not that bad. It's only like literally 2 lines difference, right? Or maybe deleting a couple lines, but you're not changing your IP routing or the IP addresses that you're assigning, so you'll see when we get there. But we did offer this ability to do auto migration for you. So you could literally take your IPQENet definition today and add, don't delete anything, don't alter it other than add the new dev number that was configured to be used on a Z17 machine. Now I'm going to jump forward to get to a chart because it's just easier to talk to this chart. So you're activating on this new IPQENet or your old IPQENet definition with a dev number and a port name. So it's unusual. Normally that would fail, but we tolerate that. And it's tolerated based on the environmental, what environment you're operating on. If you're on a Z17, we recognize, oh, this is IPQENet, and oh, they have a port name and a dev number. They want me to auto migrate their IPQENet interface into and transform it into an EQENet interface by taking defaults and all of the values that they specified that make sense. So if you're on a Z17, that IPQENet starts out in the profile as just that, the OSD channel. But then when you display it, it's going to show auto migrate it, and it's going to say EQENet and have all the various parameters. And we take what you coded for the ones that make sense, like SMC-R, fit assignment, and things like that. But if you take that same definition with the port name and dev number with our toleration APARs applied to the older, 2.5 or 3.1, and activate that on a Z16 or older box, it works just like it does today. It honors the port name, activates it just like with the old rules with the VTM TRLE, et cetera, et cetera. So with small modifications, you can do this auto migration. And that's the neat trick that we supplied to make your life a little easier if it makes sense to go there. So I'm going to jump backwards and see if there's anything else. I think I've pretty much covered everything that this was talking about. There is a footnote highlighted at the bottom. And this I think is true for any device, but once we auto migrate, or once an EQENet interface is defined either through auto migration or explicitly coding EQENet, you cannot dynamically delete and define an IPQENet using the same name. This is just a rule that's always been there, but that we're pointing at. So so if you do the auto migration, it's kind of a one-way street that it goes into that world. If you had to dynamically build another one, you'd have to change the name and most likely routing to go with it for that. So and vice versa. So if you had if you're attempting to switch from IPQENet to EQENet or vice versa, this is just the rule as it is today. Okay, as promised, here's kind of a side-by-side of what the new, so here you'll see an IPv4 EQENet definition statement that has your dev number to Baker 70, your IP address with your subnet, Here they're using VLAN 702. They've downgraded the MTU to 1500 instead of the jumbo that the OSA supports. And they're also using SMC-R. If you take a look at that same definition with IPA QENet, this is basically the same definitions, but you'll notice that, oh, look we don't have read storage anymore. We didn't have to configure that. Oh, we don't have to define inbound dynamic workload queuing. It's all built in. SMC-R still applies, but those would fall over. So it's a much simpler, smarter defaults. And you can see that really the difference is EQENet and IPA QENet and port name and devnum. That's really the difference. The bottom one I will point out, that is the migration case. If you deleted the dev number, that's what you have today. The dev number with the combo of the port name, that's the migration case where you can activate it on the new moot box or the old box, and it depending on the environment, it operates differently. And this is just kind of for completeness, showing you an EQENet 6 interface statement, the new modern EQENet 6 interface as, compared to a migration case for IPA QENet 6. Very similar, just here for completeness. Okay, so now we'll go into the converged port and how does SMC-R and RoCE v2 work today. So here, as a little bit of review, so IPA QENet, if you want to use SMC-R v2, then on the SMC-R statement, there's a few parameters called PFID and SMC-R IP address. And this is where you provision, for OSD, you would do a RoC2 PFID, a RoCE 2, which would either be RoCE Express 2 or RoCE Express 3 cards, PFIDs that you generated. And you're going to define an SMC-R IP address that's in the same subnet as your OSA, right? So when you first start that interface, let's just say OSA A, it dynamically, this interface is really you get two interfaces for the price of one. You're going to get your OSD interface that you define, and we're going to dynamically provision an SMC-R interface, EZAR, and then the TRLE name for that. So you get your OSA and your RoCE with one IPA QENet definition. So that's how it works. But in reality, that's two physical devices. It's going to activate your OSA Express device, and it's going to activate your RoCE Express device too, with two physical ports, two IO slots, etc. So now if we fast forward into what's going to happen today, now you have an OSH device with a NetH device, and it's very similar. So now EQENet is of course the new interface type that you're defining. You still configure the PFID on your SMC-R statement on that EQENet definition with an SMC-R IP address. And I stress that IP address must be in the same subnet as your OSA or OSH device. That's the rules of SMC-R. But you'll notice when we activate the interface, now it's all drilling down. You're still getting two interfaces for the price of one when you're defining it. But you have an OSH, and then the second half of the card is you have your RNIC that we're allocating. But when you drill down, it's all going to the same PCHID or physical port on the Network Express card, but it operates with both protocols. So that's the big wow factor for the IO transformation, is that you're getting two cards for the price of one in here. And it should be, reduced, same redundancy, reduced, IO slots and physical cabling and maintenance, right? So, but externally from an operational standpoint, it still operates very similarly. When you activate your OSA, the RNIC just gets built dynamically and allocates, and it'll operate functionally the same, and SMC-R runs almost identical as it did before. Okay, so this chart is just showing you the OSH with NetH with the converged NIC and RNIC, and I think it's just pointing out that these are dual adapters. And I think there was a question on from a customer previously that it's showing a single adapter, and it was a little confusing. But just for completeness, these are dual density adapters. The diagrams are only showing a single port, even though there's really two physical ports on the card. Okay, so now we're going to move forward a little bit into some of the NetStat displays, like what will you be seeing differently? So here's a NetStat dev link showing the EQENet interface for an IPv4 interface. Of course, the new type is going to be EQENet. Here is where I was pointing out what you coded was 8100 for the device number, and in this case, the actual device number that was selected was 8101. So that's where you can discern, which one we actually selected. You don't always get the lead one. Chip type is OSH. It'll always be for this type currently. The adapter gen. So this is actually an enhancement that we added. One of our lead testers. Normally, this is what's coming back from the OSA when you on OSA info. We basically get that same information a little bit earlier, and they thought it'd be nice to display the OSA generation in this display as well. So we made that handy for him, so you don't have to do the other display. Here's the VTAM dynamically built TRLE that we pass back to the stack for your convenience, so you could actually go, if you want to know, you can go over to VTAM and issue a DNet ID on that TRLE and get the information there, or a DNet TRLE equals, and put that TRLE name in there. And there's the port name I was mentioning. That's just kind of for posterity's sake. It's for future enhancements. That really has no bearing. OSA doesn't care about that name. It's just for our internal future use of that. But we do auto-generate that based on the actual device number that we selected. And here's the code level. It got a little larger. I think the OSA folks asked us to generate the whole. I think the key values of the OSA level are still at the far right-hand side, but the far left of it, I think, shows machine levels and things like that. But they asked us to display the whole thing, so we obliged and did that. Here's what I mentioned earlier about one of the changes, the usability features, is this is the total read storage. So read storage kind of went away. This is saying that this device, 8100, this EQENet device, is using currently 19 meg of read storage for inbound read processing for all your queues. And then when we get to the TRLE, you get a breakdown of what that 19 meg means. So, but here's like a one-stop shop. Is you just give you the high level. It's not a static value. This thing can change. I mean, I don't think it's going to change, humongously, but you will monitor. It won't just stay at 19 in this case forever. It will go up and down based on workload. And that's it. Okay, so this is the second part of the NetStat dev links for the IPv4. And feels very similar as before. He still has your bytes in and bytes out. But here we're pointing out that I mentioned earlier that this is basically your new OSA, and to be just like your old OSA, it has to have all the functionality of what OSA did in the past, and it certainly does. So this is showing that this OSA is tied to a HyperSockets interface in HyperSockets converged interface, and this is just showing you that it is certainly compatible in that function as well. And here's showing you that we are fully functional with SMC-R and SMC-D for internal and external RDMA and DMA operations. So just shows that we are porting all the functionalities before that existed with OSA still exist. Okay, so this is just another NetStat DevLinks display showing an IPv4 EQENet display that went through the auto migrate. And the only difference between the display we just went through is that we kind of highlighted that to say, oh, by the way, this one was auto migrated, just for your awareness. Oh, and then this is just pointing out that VMAC is required. And here it's showing you it was the origin of that VMAC was OSA generated. And now that you have to have a subnet mask, it's now required here, and just pointing that out as well. So that's a good point to mention, to drill down on. Auto migrate works pretty well, except if you don't have a subnet mask, it will fail. There are a few exceptions, and that is one of them, is that if you don't have a subnet mask on your IPQENet, we won't be able to auto-generate or auto-migrate to an EQENet. You would have to code the subnet mask on that. Okay, so here's display OSA info. So that is a very useful command. It's still applicable today, and it's we moved that forward, worked with the OSA team. So the cool thing here is that basically, you have your configuration. We auto-configure this through all the control reads and writes and all the information, all the VIPAS support, inbound routing, etc. This is basically OSA's view of what we configure to them. It's just a way, service probably really relies on it mostly, but it basically reiterates what OSA believes to be accurate of what they see the configuration as being, and we can double check that whether it was user-defined VMAC or OSA generated. All the IP assists, for you can see here at the bottom, it's all the ARP offloads. These are the IP addresses that were requesting OSA to ARP for us and things of that nature. But this is a very nice display. Here you can see the generation and the code level that they supported. I think this one was mocked up a long time ago, but essentially this moved forward. The interface packet drop kind of in the middle of your screen, that is a function that was preserved. It was added late to OSA Express, like I think through an APAR maybe a year or two ago, but that moved forward. The one thing is that interface packet count is going to be for the whole port. It's not just your logical use or your device. This is the whole physical adapter, what they're feeding to us. So that's what that represents. Okay, so now the TRLE display, the look and feel is still very much the same as before, but it's enhanced. So you'll see, let's point out some of the footnotes, but basically with the new Enhanced QDIO architecture, there were some requirements that everything, instead of having these control channels, we have queues, and there's architecturally is up to 32. I think on Z17 we actually were allowed to use up to 16 of these queues. The only architectural requirements is that Q1 is the control read, and Q0 is control read, and Q1 is control write. After that, you can put them in any order as you want. ComServer decided to make the outbound writes queues, EQDIO Q2, 3, 4, and 5 as your 4 writes at the bottom of your screen. And they are the same as, with WLM priority queuing, we still write your data to this specific outbound write queue, and OSA will provide, higher, priority to priority 1 over priority 2, et cetera, just as it does today. It's a little odd that you can see we tried to put the priority 1, 2, 3, and 4 to dictate that, but it's really, EQDIO slot 2, 3, 4, and 5 that represent that. It's unfortunate it didn't work out 1, 2, 3, 4 to make it a little bit easier in your head, but you get the idea that priority 1 is, the highest priority work, and priority 4 is the least priority work that is assigned with WLM priority queuing in this case. Now, if you put focus on the middle of the queue, here's then after the write Q5, then that's where we defined all of our inbound read queues. And as I said, we always get primary and bulk. You're always going to have at least 2 queues, and all the remaining queues kind of come and go based on whether you have a configuration, whether you're supporting Enterprise Extender or you have a dynamic Viper for ZCX, et cetera. A new queue, we're not talking about too much, but if you have QDIO Accelerator and a few other options like datagram forwarding and VMAC route all, then we'll instantiate a new queue for QDIO Accelerator. It's basically a new default queue that if the workload isn't steered to any one of the other queues, it's kind of a default queue that, it must be data that's going through me. So it makes our QDIO Accelerator code work a little more efficiently instead of routing through the whole primary queue to find data that's destined to the stack versus stuff that we're just going to forward on. So it makes our forwarding logic much more efficient in the stack. And that's a new queue and a new enhancement we made during this release, along with all the other queues. We still support all the other queues as before. So the control paths on the read queue is 1 meg and it doesn't grow. So the min and max, that's just a static. We don't expect tons of control data flooding us, but 1 meg is, a generous amount to support the configurations. But the primary and bulk queues will always be 8 meg. It will never go less than that, but it can grow. That max column is actually a high watermark column that's shown you. In this case, it has never grown beyond that. But based on workload, it has the ability to creep up. It's just always trying to stay ahead of the adapter base, make sure that there's enough reads replenished. So if there's a spike in data, we'll see that it's using more, and during our interrupt, that's where we pulled all the data out. Oh, it used a lot of that queue. I better expand it by a little bit. And we expanded by like 128K bytes at a time. So that's how we, in chunks of that. So it's about 1/10 of a meg each time. And then once we see that we're not using it long, then we'll contract it though. So if you ever see a max or a high water mark above that, then you had some busy times and it was expanding, but it does, expand and contract dynamically for you. All the other queues start at 4 meg. They'll never go below 4 meg, but then they can expand and contract just like the other queues as well. But that's so if you sum up all of those, the 1 meg, 8 meg, 8 meg, and then you take the cache read storage of 3 meg, that's like stuff that we need inbound to route the data and have available buffers to replenish the ring. That summary, that total read storage is 28 meg. That is the value that we put over on your NetStab dev links that matches over there. So that's basically, if you want the details, you can look here in the TRLE. If you just want a one-time value, the NetStab dev link seems to be the place to go. Okay, so now we're getting near the end of the presentation. So this is kind of basically where are we, how far did we get, or what are some of the limitations or guidance we want to pass to you? So basically, there's no EQDIO support for z/OS 2.4 or if you're a ZVSE client. We did support the NetH or the RoCE side for migration purposes for z/OS 2.4. So if someone's interested in that, we do have APARs that are going to be made available this week for SMC-R version 1 support only. I'm not sure that applies to anyone. SNMP support for OSA or OSH. We couldn't contain it for GA, but we're targeting to get that deployed and rolled back into the field releases this coming September. OSA NTA, we've had a lot of customers, between OSA NTA and QDIO Sync. These are not in the GA version. These are many customers are asking for it. So these are on the agenda and they'll be going forward. I can't promise it, but there's a strong inclination that we will be developing these. QDIO Sync, I could almost guarantee we're doing that. OSA NTA is a bigger ticket item that'll have to get on the agenda, but I believe that we will go forward with that. It's under advisement that we are considering that for the next release with, I'm sure, rollbacks. Okay, so for NetH PFIDs, some of the guidelines when the sales guys are going out with is not oversharing it. So since this adapter is doing a lot of work, 16 from a z/OS perspective, there's no enforcement. There's just guidance that you shouldn't configure more than 16 NetH PFIDs to be utilized per adapter per PCHID, that is, going out to 3.1. Okay, the next bullet is basically talking about if you're running z/OS in a ZVM switch environment as a guest virtual machine, in this configuration for technical reasons, you must configure OSA Express. This is just a point-in-time statement. Eventually, ZVM will support that where you can use Network Express, but currently ZVM doesn't support this configuration, and you'd have to order OSA Express instead of Network Express to support z/OS as a second-level guest. And the last bullet I kind of mentioned is QDIO Accelerator is a supported function in Enhanced QDIO, but it's limited to Enhanced QDIO to Enhanced QDIO devices only. And I think we're getting near the end. This is just a little nice chart for these are the enablement APARs or the toleration APARs that you'll need for COM server. And we do have a dependency on iOS APAR, and those are listed there. The APARs will, IFREC each other to make sure you put them both on. We'll also call out the iOS APAR when you apply the VTIM and COM server PTFs. I think that's it. I don't know if we had a lot of questions during the chat I'm sure there's lots of information and it's a little overwhelming. You do have our PDFs and you have our emails, so please feel free to ask us questions, email us questions after some of this. You have time to digest some of the information that we've presented today.
Again, to remind you, in the appendix, Randy's got some really good examples. So we didn't cover that because for time purposes, but again, just encourage you to look through there. You'll see some very handy information, but
I'm sure it's just I understand that this is a big presentation. There's a lot of information being thrown at you. So I fully expect that when you go back, you'll have questions. And as I said, our emails are on the front page. Pete, please feel free to ask away.
Yeah, and I don't know if you want to scroll through the charts real quickly, the appendix, to show just what's there. You don't have to stop at them, but just slowly scroll. So, yep.
Yeah, so this is the chart that Jerry was talking about. This is a nice compare and contrast between IPQENet and EQENet, basically all the values in it. There's a little bit of a explanation of why it doesn't apply anymore. So this is a nice reference chart. This is a continuation of that, of all the parameters. And the same thing applies for IPv6 versions as well. Here, this is pretty interesting. So this is kind of some of the, we're not, HCD or IOCDS gurus here, but we did, for completeness, give you some examples of how you define the NetH and OSH, PCHIDs and FIDs. But there's, kind of detailed information here as far as what each example shows. So that's a nice reference material. Here's kind of talking about some of the IO configurations. We kind of alluded to, like, if you didn't have any OSHs defined to the LPAR at activation, this is the failure message. Here's where, if it's online, where you'll see if it's offline, the device, we kind of hang out, the start stalls, and you'll see a message saying that subchannel is offline. And then later on, when you online the display, it'll just kind of pick up dynamic ENF, picks it up, and it continues with activation. And while it's in this limbo land, if you display the TRLE, it'll show the state is offline. You'll see from a netstat dev links that it's not active and the device status is starting. You see starting, that means your activation is stalled for whatever reason in the VTAM. In this case, it's stalled because the device is offline. And as soon as you do it online, we just pick up where we left off and continue activation. This is just talking about the various RoCE support that we did. So OSD, you can pretty much use any NetH device, but on OSH, you have to use a NetH PFID from the same physical port or PCHID. We will fail that if it's not. We do not support, we considered it for the supporting non-converged PCHIDs, but we don't have a use case in handy to, basically, justify the extra work for that.
Yeah, so let me jump in, make sure we get this question for time. Someone asked, did I understand correctly, ZVM does not support Network Express? No, I'm sorry. Network Express will be supported by ZVM. And what we're saying here is that if you want to put ZOS on a vSwitch, which is unusual, a lot of customers won't do that. vSwitch is typically for scaling large number of guests. But if you do for test purpose or what have you, if you put us on a, it must be OSA Express, because ZOS only supports layer 3. And so for the vSwitch, so for a vSwitch configuration, using ZOS as a guest, you still must use OSD. But if you're just using it for Linux support or other support, yes, OSH is supported, but not for layer 3 users like ZOS. So ZOS requires OSD for the vSwitch support, and that'll be corrected in a future ZOS deliverable, ZVM deliverable. Hopefully that makes sense. Only when ZOS is on the vSwitch.
And I think it's pretty much just various displays showing you more of the IPv6 information, auto migrate for IPv6, and there's some TuneStat displays to show that we still support TuneStats for the new device. And that's it.